everyone, this is Mrs. Hanson here. We are going to talk about how to create a model using polynomial functions. So this is the last part of your assignment in lesson 2-2, where I assigned the homework assignment for this is 43 through 49. And I am currently on page 103, and I'm looking at real world example number 7. So I'm in your textbook on page 103 and I'm looking at example 7. And it says to refer to the beginning of the lesson, the average personal savings as a percent of disposable income in the United States is given in the table. And they give us a table of values. One column, or one row rather, contains the year and the other contains the percent savings. So I'm going to go ahead and model this data. And I'm going to type in the years into my first list, and I'm going to enter the percent savings in my second list. So here I'm going to go to enter data. I go to the stat button right here, and I press edit. And some of you might have some data in your lists from previous questions that we've done in class. So I'm going to go ahead and clear out those lists by placing my cursor on L1, pressing clear, and then arrow down. And I'm going to go up to L2 and press clear and arrow down. And now my lists are empty, so I'm going to go ahead and enter the data from the book. So it says that we have the year 1970 as our first year, 1980 as our second year, 1990, 1995, 2000, 2001, 2002, 2003, 2004, and 2005. And in list 2, I'm going to enter the percentage of savings. So I'm going to enter 9.4%, 10, 7, 4.6, 2.3, 1.8, 2.4, 2.1, 2.0, and then negative 0.4. Oops, made a mistake there. So I'm going to go back to stat and edit, and in that last entry, I'm going to type in negative 0.4. Enter. Okay, so we have our data entered, and part A of the question says create a scatter plot of the data and determine the type of polynomial function that could be used to represent the data. Well, if you remember from the last time we did scatter plots, after I've entered my data, I should first make sure that my stat plot's turned on. So I go to second y equals, that's where my stat plot is. I'm going to press enter and make sure that my plot is turned on. You'll see plot 1 up here highlighted, and we want to make sure that we choose a scatter plot. We have list 1 and list 2 with the marker here, and we're going to go to the window. Next. Okay, and I'm going to set up my window. Now remember, our x values were the years between 1970 and 2005. So I'm going to say 1965 to 2010 because I'm going to give myself a little bit extra room beyond 1970 to 2005. And I'm going to make my scale count by 5, so every tick mark is worth 5 years. For y minimum, for the y values, we are measuring the percentage of savings, and those range from negative 0.4 all the way up to 10. So I'm going to say negative 1 all the way up to, let's just say 12%. Even though that's a little bit bigger than any of the percentages we entered into the table, that's giving us a little extra room on the graph. So now that I have my stat plot turned on, I have an appropriate window. I'm going to go ahead and graph the scatter plot. So this is what part A looks like. Part A says create a scatter plot of the data and determine the polynomial function that could be used to represent this data. Now to me, we have 4 options here for a polynomial function. We have a linear function, a quadratic function, a cubic, and a quartic. Now the degree of a linear function is 1, and the degree of a quadratic function is 2. A degree of a cubic function is 3, and our degree of our quartic function is 4. Now, based on the way this plot is represented on our graphing calculator, it looks like there's a little curve or bend here, and that this right here is a turning point. And so if I have one turning point in my graph, then that means that the degree of my polynomial is most likely 2. So I'm going to go ahead and check quadratic and make sure that that is an appropriate fit. I'm going to go to Stat and over to Calc. And this is the same place we calculated our power regression, except I'm not looking for a power function this time. I am looking for a polynomial. And again, my 4 options for polynomial are linear regression, quadratic, cubic, and quartic. So option 4, 5, 6, and 7. Because my graph had only one turning point, I think that this might be a quadratic function. So I'm going to choose option 5. In the X list should be L1 because that's where I entered my X values. In the Y list, I entered my L2 because that's where I entered my Y values is in list 2. I'm going to store my regression equation, vars, Y vars, function, Y1. I'm going to store that equation in Y1 in my equation editor up here. And then I'm going to enter calculate. Now, notice here that I have an r squared value of 0.96. Now, if I have an r squared of 0.96, I need to find my r value, which is my correlation coefficient. So I'm going to do a little bit of math here on the side, and if I square root 0.96, because r squared is 0.96, if I square root that, the square root of 0.96 should give me the r value. So if I square root 0.96, I'm going to go ahead and do that on my calculator. Square root of 0.96, I get 0.979, or maybe even approximately 0.98. So my r value in this case is 0.98, and the r value tells us the strength of the model, or the accuracy of the model. And so we know that there's a strong correlation, 0.98 indicates a strong correlation between the year and the percentage of savings that we have. And so it means that this quadratic is a pretty good fit for the set of data that we entered on our scatter plot. So I'm going to go ahead and I'm going to look, just based on this r squared value and then square rooting both sides here, I got an r value 0.98. I'm going to go ahead and look at the graph, and if you look at my equation that's graphed over the top of my scatter plot, that's a pretty good fit. There's a few points around here, up here, and in here that aren't exactly on the line, but those points that are not on the curve or on the line or on the equation, those aren't very far away from it. So that is what gives us the visual for that correlation coefficient, for that r value. The higher your r value, the better fit that equation will be to your data. So I'm going to go ahead and say that our function is a quadratic function. And if I go back to my main menu, if I quit out of there, out of my graph, notice that my equation's gone. I can go back and grab that by going to Stat and Calc, option 5, and this time I'm not going to store it because it's already stored in my equation editor up here at y equals, and I'm going to press calculate. And this time I'm going to write down this quadratic equation. This is my model. A mathematical model is an equation that fits a set of data. So I'm going to go ahead and rewrite this equation up here, y equals ax squared plus bx plus c, but this time I'm going to substitute my a value, my b value, and my c value in the appropriate location. So if you go back to, once you've written this down, that's part B, right? The polynomial function to model the data set. And it said round each coefficient to the nearest thousandth. And the nearest thousandth is 3 decimal places. So my equation that I should be writing on my paper right now for part B is y equals negative 0.00 x squared plus 34.051x plus a negative 33,563.428. That would be my equation because, again, I'm rounding to 3 decimal places as instructed in the text. And it also says state the correlation coefficient. Remember, I already calculated that. I squared, the correlation coefficient is r. And if you know r squared is 0.96, you square root both sides, and that is what gives you the r value or correlation coefficient. Now, in part C, it says use the model to estimate the percent savings in 1993. So, if we want to model the percent savings in 1993, that means that I take my equation that I just wrote down in part B and substitute in 1993 for x. Now, I'm going to go to my table setup. There's a little bit faster way to do this. I'm going to go to my table setup and turn my independent variable, which is x. I'm going to change that to ask. And when I do that, once I've changed this setting to ask, I can go to my table and I can type in 1993 for x. Okay, so what this is doing is it's saving me the time of inputting 1993 into my equation for x and finding y. So again, to set up that setting, I go to table setup, make sure that the independent variable is on ask, and then I'm going to go over to the table right here. So press second and then graph, because that gives me my table. And if I enter 1993, it tells me that my percentage of savings was just under 6%, so 5.94%. The next part of the question, it says use the model to determine the appropriate year in which the percent savings reached 6.5%. Okay, so this time we know that y is 6.5%, but we want to find the year that's going to happen. Now, unfortunately, we're not able to plug in y values and find x in the table. So the way that we find x when we know y is by graphing another equation here. So here's our model. This is our quadratic model for the data. And this time I'm going to go ahead and graph y equals 6.5. So if y equals 6.5% and this is the model for my data, I'm going to graph that line y equals 6.5%. And I want to know the year when this model, this curve, this quadratic function hits 6.5%, which is right here. And to figure that out, to figure out the exact point where where this model here hits 6.5%, which is in red, I'm going to go to the Calculate menu and choose Intersect. And I can go ahead and place my cursor right on the intersection of those two functions. Press Enter on first curve, then it's going to ask me second curve, press Enter on guess, and it gives me the exact time or year when y, our savings percentage, is equal to 6.5. So we have the year 1991. Somewhere in the year between 1991 and 1992 is when the savings percentage was 6.5%. All right, so we've answered the question. You can go ahead and rewind if you need to rewatch part of this, or you could also watch it, rewatch it as you are doing your homework if you have questions on things that I did on the calculator.